写下半导体的传奇。60年的影响力奔转全世界，机体电路的浪潮将继续勇往直前。
IC60邀请您一同参与。
现在无所不在，未来无限可能。台湾的远见写下半导体的传奇。60年的影响力奔转全世界，机体电路的浪潮将继续勇往直前。
IC60邀请您一同参与。
现在无所不在，未来无限可能。台湾的远见写下半导体的传奇。60年的影响力奔转全世界，机体电路的浪潮将继续勇往直前。
IC60邀请您一同参与。
现在无所不在，未来无限可能。台湾的远见写下半导体的传奇。60年的影响力奔转全世界，机体电路的浪潮将继续勇往直前。
IC60邀请您一同参与。
现在无所不在，未来无限可能。台湾的远见写下半导体的传奇。60年的影响力奔转全世界，机体电路的浪潮将继续勇往直前。
IC60邀请您一同参与。
现在无所不在，未来无限可能。台湾的远见写下半导体的传奇。60年的影响力奔转全世界，机体电路的浪潮将继续勇往直前。
IC60邀请您一同参与。
现在无所不在，未来无限可能。台湾的远见写下半导体的传奇。60年的影响力奔转全。
将在5分钟之后开始，请您尽速入座。为了尊重演讲者，请容我们提醒您将手机调成静音模式，感谢您的配合。大师论坛下午场次将用英文以及中文进行，论坛提供同步口译服务。如果需要租用翻译耳机的来宾，请到场外凭证件租借，谢谢。Good afternoon, ladies and gentlemen. Our program will begin in 5 minutes. Please take your seat. At this time, may we remind you to silence your mobile devices. The afternoon session will be conducted in English and Mandarin. Simultaneous interpretation service is provided at this forum. For those who wish to use the service, please rent your interpreting headsets at the reception desk. Thank you. 论坛下午的场次即将在3分钟之后开始，请您入座。请容我们提醒您将手机调成静音模式，感谢您的配合。大师论坛下午的场次即将用英文以及中文进行，论坛提供同步口译服务。如果需要租用翻译耳机的来宾，请到场外凭证件租借，谢谢。Good afternoon, ladies and gentlemen. Our program will begin in 3 minutes. Please take your seat. At this time, may we remind you to silence your mobile devices. The afternoon session will be conducted in English and Mandarin. Simultaneous interpretation service is provided at this forum. For those who wish to use the service, please rent your interpretation headsets at the reception desk. Thank you. Ladies and gentlemen, welcome back to IC60 Master Forum. This morning, we looked back 60 brilliant years with industry pioneers who had made tremendous contributions in IC development. In the afternoon, we invite industry leaders to shed light on future. And now, without further ado, please join me in welcoming Deputy Minister of Ministry of Science and Technology, Dr. Yojin Xu, to deliver his welcoming remarks. Please welcome Deputy Minister Xu.
Honorable speakers, distinguished guests, ladies and gentlemen, good afternoon. Welcome to the afternoon session. In 1965, Gordon Moore proposed the Moore's Law. You heard that this morning. He predicted the transistor count double every 18 months. And I was told it's based on two technology law to make this prediction. So that's a prediction about the future. In year 2012, there's a breakthrough in neural net we call AlexNet. And they claim the CNN convolution neural net, if the deeper of the neural net, you can do more things. You can realize and understand more with the neural net. So here this morning, Paul showed the chart, right, from the OpenAI, that the demand for computing double every 100 days. Every 3.5 months, the computing need double. Okay, that's what Paul mentioned this morning, that we climbed the small mountain in the past 40, 50 years. There's a much bigger mountain you'll climb in the next 60 years. Okay. Taiwan built a stronghold for semiconductor in the past 60 years. We have a complete supply chain from upper, middle, and lower stream in the industries. And we have the IC design, manufacturing, fabrication, and packaging and test. All the industry, all in our science park. Based on IEK, in year 2017, the output value of semiconductor in Taiwan is 2.46 trillion Taiwan dollars, which equivalent to 81 billion US dollars, which rank number 3 in the world. And in the first 6 months, based on our data from the science park, our semiconductor growth is 15.72% in the first 6 months compared to the last year. So you can see that the big increase in the growth in the semiconductor area. So I want to do it here. So Taiwan, we have a science park. We have a north, middle, and south science park. So this week, this Friday, I'll bring our director of the 3 science park to Silicon Valley. And in the Hilton, Santa Clara, we will have the forum. We'll tell our audience what is our science park, what's the focus, okay, how I'll click about our science park. So for those who are in the Silicon Valley, welcome to join our forum. So this morning, all masters make a significant contribution, will make a outstanding talk. And in this afternoon, we have 7 talks, all from companies, distinguished companies, the CEOs, founders, or top executives. They are talking about what they see in the future. So without further ado, I will leave the forum to all these speakers. Thank you.
Thank you, Deputy Minister. Please remain on stage. 请次长留在台上，我们要进行合照。And may I please invite all the speakers in the afternoon session onto the stage for group photos. Please welcome Dr. Mark Liu, Chairman of TSMC, Mr. Yuanmao Su, Vice Chairman and Deputy CEO of Winbond, Mr. S.C. Chen, Co-President of UMC, Dr. R.D. Jies, Chairman and Co-CEO of Synopsys, Dr. Tian Wu, President and CEO of ASE, Dr. Richard Gacho, Executive Vice President and Corporate CTO of Lam Research, and Dr. James Frey, Business President of Dow DuPont. Could all the guests of honors on the stage come closer to the center and look at the cameras in front of you? This is a rare opportunity that we have business leaders in the wonderful semiconductor industry gathered together for the IC60 Master Forum. Please give us a thumb up. Let's together wish IC60 Forum, Master Forum, a great success. Thank you so much. Thank you. Please return to your seats. And once again, thank you, Deputy Minister Xu, for your kind words. Thank you. So now, ladies and gentlemen, to look into the future, we will start from the perspective of Foundry. We're very honored to have Dr. Mark Liu, Chairman of TSMC, as our speaker. Dr. Liu is currently Executive Chairman of TSMC. Prior to assuming this post, he was President and Co-CEO of TSMC from November 2013 to June 2018. And before that, he served in a number of executive positions at TSMC, including Senior Vice President of Operations from 2009 to 2012. The topic of his talk is IC Technology Innovation Outlook. As Dr. Liu will be ready soon. And ladies and gentlemen, please put your hands together and welcome Dr. Liu.
Good afternoon. Thank you for coming. And I want to give this talk. Actually, my title has slight change. The title will be IC Technology, the Roadmap Going Forward. The purpose of my talk is give you an idea that semiconductor industry has never been, the future of semiconductor industry has never been so bright before. Secondly, I encourage young people to join this industry. Thirdly, as we heard about Morris, this is time to invest. Not just invest in Taiwan, but also invest globally on the semiconductor. Actually, the semiconductor industry has been coming to a very special phase. The application of artificial intelligence, 5G communication, and AR, VR, and automotive, there are vast amount of applications today. This is the most exciting period of the semiconductor history, the way I see it. However, ITRS, International Technology Roadmap for semiconductor, unfortunately have sunset in 2016. So the industry has lost its direction. Where should we go from this on? So this is the reason I want to tell you, while we are in the midst of heavy investment, I want to tell you what's the roadmap going forward. These first few graphs is for the young students and young engineers first came to this industry. A lot of them in the other room, okay? Technology drives our societal change. This is the 3 centuries. Just look at from the population migration perspective. The steam engine and the industry power factories really bring all the farmers into the cities. In the 20th century, the electrification and the combustion engine then give people mobility and bring the people over to the suburban areas. Coming to this century, the semiconductor technology and information technology developed so fast that it really doesn't matter where you are. Anything you do has a global impact. And all the economy has becoming information-based, knowledge-based, and service-based. I want to put our perspective, give it a little bit bigger, is society embrace technology advances today. I plot this as a world global GDP, and horizontal is a year, and I marked several of technology innovations. First of all, how lucky we are. Integrated circuit was invented in 1954. And we are at the threshold of the world GDP. I think we are the most fortunate generations in the 100 years of history. But the point I want to show is that the innovation pace is gathering speed. From the digital computer to portable computer takes 30 years. From first commercial mobile phone to first smartphone takes 10 years. And the recent driving autonomous vehicle first drove in the desert to now, actually they are capable of driving with the driver sit next to it, on it, with urban course. Just take 2 years. There are many examples. For example, the voice assistant devices, I think, appear to your living room, your bedroom, is very quickly, in 2 or 3 years. And this technology embrace speed is even faster as we look further. From the for the semiconductor adoption, it has changed indeed in the past few tens of years. First, it find its application in mainframe computing. Then it moves to personal computing. Then it comes in about 2010, it moves to mobile computing, where smartphone, where everybody has one. And then the way we look at it from now on to the future, it will be ubiquitous computing. Not just computing by instruction, but rather the computing devices will communicate with computing devices. This we coined ubiquitous computing. I think we coined this 4 years ago because we see our foundry growth actually driven by these 4 areas. First is smartphone, or probably new mobile devices, and also by high-performance computing, and by the automotive, and by IoTs. Actually, the society has high expectation to our industry. We have cars driving, autonomous car driving in an experimental way. Drivers cannot leave their driver's seats, but some of the drivers tried. But the society is expecting the self-driving car to come to our life. But we know, really, if you need an autonomous driving car without a driver, the computing power has to be 100 times more than what we can do today. And let alone the 5G communication and all those protocols to happen. Now I want to talk about the semiconductor roadmap. The first roadmap is the scaling. Semiconductor scaling will continue. This is the history of the semiconductor scaling. In the past 50 years, it scales 1,000 times. Today, we have 7 nanometer in production. This is the first time in semiconductor history that a leading edge technology is available to all market segments, be it computing or be it automotive, be any kinds. So the innovators just first time they're trying to jump in and they coordinate each other. I believe from this on, the innovation speed will even collect their speed because of the availability of the foundry technology at the forefront. We have program going down, 3 and 2. And if you think 2 is too small, think about it. It's 20 angstrom. It's a pretty big number. This scaling will come about with a lot of innovations already happening and already in production, but still needs further investment. First, the EUV lithography, and new transistor structures like FinFET, and new material like high-K metal gates. First of all, talk about lithography. In early 1980s, if you trying to see the end of semiconductor innovation, just think about it. In early 1980s, people think optical lithography is coming to an end. That's about 1 micron technology. And a lot of research and development on X-ray lithographies, E-beam lithographies. But since then, how much innovation has occurred beyond our expectation? The wavelengths continue to decrease. Recently, the breakthrough of EUV has shown that lithography is no longer the limiting factor for the scaling in the next few generations. Because the wavelength, it has a more than 10 times reduction. Transistor scaling will continue. We have a break away from the planar transistor structure and its scaling. It gets to 3-dimensional, FinFET, and it's going to nanowire technology. And the mobility wants to further increase, so there will be different material research and development needed for the transistor scaling, and germanium being one. And there are other 2D materials, graphene or the molybdenum disulfate. That's what I think I want to show next. But in this transistor scaling, in the past, performance, power, and area used to be the metrics. Today, energy efficiency become the new metrics. Everything we do is to reduce the energy because their density is large enough. A lot of parallel processing are capable. What we need to do is reduce the energy. Your phone in your pocket is about 5 watts. And in that, typically when you read email, about 50% are power consumed by electronics. But if you download video, probably goes to 70% of the power is consumed by electronics. And data center, where constructing a data center is only half of the cost. The rest, the majority part, is still consuming the electricities. So no matter in mobile devices or in data center device today, energy effectiveness is the matrix. That further exacerbated by the new innovation of artificial intelligence. That is, we have to move the data, not just for the computing, we need to move the data in and out of the memory storage. And I show these 3 flavors of the neural network. And all of them, most of the computing energy is consumed by the memory and the idle power waiting for the data come from the memories. So memory introduced a huge barrier for further reduce the energy efficiency. This is what the current solution it is. The current solution is courtesy of NVIDIA's is a machine learning for training. And it has a GPU. In order for the memory to, first of all, the memory needs to be very close to the logic device. Memory needs to have a wide bandwidth. Memory array needs to be highly parallel accessible. And here we show the 2, what do we call high bandwidth memory, 4 of them. And each of the memory is stacked in this package. Within the package, each of the HBM is 8 layers of DRAM stacking up together. It's connected. And between the memory and the GPU, we use the CoWoS, our integration technology, advanced packaging technologies. Going forward, this is an important roadmap we are developing. In CoWoS, while we continue to packing the interconnect density even higher densities, but also there are areas that today we are only at 2.5D. The future will go to true 3D, where memory and logic is being stacked on top of each other to further reduce the memory power consumption. And going forward, the monolithic 3D will give you another 100 times of the packing interconnect density we will have. This advanced packaging not just solve the memory barrier or memory wall problem, it also gives you a roadmap for the heterogeneous integration. That is to integrate all the embedded flash, sensors, high voltage power, and analog 3D MEMS, put it into logic to improve the system performance. And that is mostly done by the monolithic already. Some of them temporarily done by the advanced packaging. And it has a lot of application already coming to the market. The third axis is the software and hardware co-design increase. Let me put a layman language. This is architecture innovation, or liberation of computing architectures. We've been living the CPU for many years. At the time, CPUs has the same architecture for almost 30 years. And it sits on the same motherboard in the center of the motherboard. The rest of the innovation only carry around that. But then, more recently, the special purpose CPU is come about. GPU, DSP, including the cryptocurrencies, innovation of highly parallel processing computing devices. Going forward, the domain-specific architecture will come about. For each application, the domain, the architecture will be adjusted. And in order to reduce the improve energy efficiency. And this domain-specific is potential to increase 1,000 times compared with the old CPU architecture. And the problem is how to make it more flexible. And that is what industry is working on, how do we reconfigure the hardware on the fly using the software and create a language for that user can do that. It is close to the TensorFlow you'll be able to compile into using the GPU or CPU today. That type of software development. And this is today's SoC design, has a number of accumulators, accelerators. Actually, accelerator is the highest growth momentum we see in the high-performance computing. In the future, the SoC will contain a sea of fine-grained accelerators, and is coordinated by the GPU and the DSP and the CPU. Finally, I want to summarize my talk. The roadmap we see, we no longer sitting on the same architecture, solely depend on the scaling. Logic scaling will continue. Pace may be slower, but innovation we see continue pouring. And it also include the on-chip memory, that is to reduce the memory power consumption. Another axis is 3D IC. 3D IC to drastically be it homogeneous, put in the memory or other logic chips, or heterogeneous by putting different IC from different application, even from different foundries, so you can be able to put into a smart devices. And lastly is the architecture innovation, the software and hardware co-design, be able to drastically improve the energy efficiency. We expect these, if we parallel develop these three axes, our computing density per unit areas is much more than 2 times for every 2 years can be accomplished. So that's my talk. I hope the industry embrace this as a start, hopefully to put it into a more specific roadmap so that all the investment can be synergistic. Thank you very much.
Thank you, Dr. Liu. Thank you for your insightful talk. Thank you. The next topic we're going to explore is IDM, Integrated Device Manufacturer. It is our privilege to have Mr. Su Yuanmao from Winbond Electronics Corporation, one of the leading IDMs, as our speaker. Mr. Su is currently Deputy CEO at Chairman's Office at Winbond Electronics Corporation. Prior to assuming this position, Mr. Su held a number of executive management positions at Winbond. The title of his talk is Keep Your AIoT Data Safe with Secure Memory Solutions. Please welcome Mr. Su.
Hello， 各位现场嘉宾午安。Good afternoon, ladies and gentlemen. It's really an honor to be stand up here with so many distinguished executives from our and leaders from our industry. My name is OM Su. I'm from Winbond. And in case you don't know much about Winbond, we are an IDM specialty memory company. We're making DRAM, NOR flash, and small density NAND flash. And in last year, 2017, we shipped over 4 billion units of product to the customers. Our company was established in 1987, 31 years ago. And if I'm not mistaken, that's exactly the same year TSMC was founded. And today, TSMC is about 25 times bigger than Winbond in revenue. And also, I don't have so-called the technology to talk about, so my speech today is about the importance of data security in AI era. And I will share with you the Winbond solution that addresses the challenge. So the presence of artificial intelligence has undergone another resurgence in past few years. So it now goes beyond science fiction or television show, and it penetrates to our daily life, making our lifestyles more comfortable, more enjoyable, more organized, and safer. And as the technology continues to evolve, there has been a lot of controversy as to how it would bring to human beings. And a question most frequently asked is whether or not the AI is going to take away our jobs. The answer is probably yes, it will take away our job in certain fields. But in the meantime, the realization of AI is expected to create new jobs, boost our productivity, and add to global economic growth. The idea of AI is not new. It has taken nearly 70 years for the right combination of all the factors to come together to transform the AI from a mere concept to increasingly ubiquitous realities. And besides all the algorithm, it is believed that the cutting-edge semiconductor technology inside the hardware are the key elements that have been driving and powering the advancement of AI. So shown here from the edge to cloud, you can see example of AI processors such as CPU and GPU and TPU and FPGA from leading companies that provide the computing power necessary for the AI training and learning. And now shown here are those high-speed, high-bandwidth DRAM and storage devices that are also indispensable in the typical AI system architecture. So the AI in present day is often referred as nano AI, where it outperforms human beings in certain specific jobs. The long-term goal is to drive toward general AI to do as much cognitive work as human beings can. And this movement will be the primary driving force for the future semiconductor demand growth. So shown here are two sources forecasting exponential revenue growth for the next few years. The first one is from Tractisia, who forecast about $40 billion US dollar revenue for AI processor in year 2025. And the other one is from UBS, who forecasting or predicting an even more aggressive number at $35 billion US in year 2021. And not included in this chart is the same revenue trend in memory devices, DRAM and NAND flash, which are companion to the AI processors. So the AI has extended beyond the cloud into edge computing to solve the problem of internet congestion, the real-time response, the personal privacy, and data security, and others. And the main reason behind this is the explosive data growth from billions of IoT devices. Or you may say that the rapid rise of the smart to becoming intelligent IoT devices is directly related to the adoption of edge computing. Or in other words, edge computing and IoT devices, they go hand in hand together. So the proliferation of IoT devices come with the explosive growth in data generation that also creates the new data economy. But on the other hand, along with the data management, the data security has become a greater and greater challenge and could put your business or personal privacy at risk if not managed properly. The cyber attack, cyber security is a well-known problem, and I'm sure you have read news about hackers breaking into companies' intranet, stealing business secret, and demanding huge ransom. You may also read report about the cost of damage done by cyber attack per year. So here I share two quotes from IBM CEO and Wall Street Journal for your reference. And my following slide will nail down to the data security issue at the edge side, and I'll share with you how Winbound solution can help. Okay, there are many ways a hacker can attack your data. So I'm going to share with you a few straightforward examples. So in this system diagram here, showing an AI processor connecting to a non-volatile memory device which store your critical data, such as your password, your encryption key, your credit card, your bank account, and even your formula of your system design. So data can be subject to the data can be subject to attack or eavesdropping by the following example, both in transit or at rest. Sniffing is commonly used by prime hackers who can capture and interpret the information transmitting over the communication channel. Man-in-the-middle attack, where hackers secretly relays and alter the communication between your SoC and the memory. And unauthorized read-write right at the memory side is another common problem, where your data in the memory could be changed, could be read, could be erased by hackers who are familiar with the device command protocols. And finally, a determined hacker can even physically disassemble your device at the edge and trying to, in an attempt to probe into the internal circuitry to learn or alter the content. Okay, so Winbound Trust Me as a solution. Trust Me is a platform of Winbound secure flash memory solution. And it is to address the data security issue that I just described in the previous slide. And essentially, there are 4 key technologies in IP to achieve the purpose. So they are encryption, decryption, integrity protection, tampering resistance, and authentication. So the bus encryption here can prevent the hacker from interpreting the message snipped on the communication channel. And with the integrity protection on both sides, meaning the AI SoC and the memory side, any modification to the message will be detected and prevent the relaying or altering the communication in between. And the authentication can guarantee that any read-write command from SoC to memory is authorized. And for the anti-tampering with the so-called DPA, SPA resistant technology, and also the active shield, all are built in to defend a physical attack. So what's Winbound Trust Me? Trust Me stands for Trusted Memory Environment that enable trust by enhancing advanced flash memory with smart card security technology. Okay, let's look at this system diagram one more time with the AI SoC and talking to the memory. So the secure IP residing in both SoC and Trust Me Secure Flash establish a secure link in between. So any transaction that failed authentication will be aborted to prevent unauthorized access. And the secure IP also encrypts the entire payload with one-time setting key to ensure confidentiality of data in transit. And the integrity protection, the technology of MAC and CRC is also built in to ensure the consistency of data both in transit and at rest. And all the Trust Me product are built in, enhanced with anti-tampering technology that can fend off any physical attack from the hackers. Okay. So the secure IP and the secure flash here together, combined together, create a Trust Me secure subsystem. Okay, this is all one. Okay, it's not supposed to show this way. Anyway, so far I have explained how our Trust Me platform can deal with so-called the data security threat between the AI SoC and the memory. But what does all mean in practical terms? So let's look at this traditional embedded system with the embedded flash inside to store the data to protect your secret. Okay? But the embedded flash here inside your SoC is not physically accessible, so making the hacking activity physically not possible. So this is good. However, such implementation has drawback. First of all, the embedded flash, the size is fixed, so it's not scalable to different requirements or applications. And secondly, the extra cost associated with embedded flash is enormous, particularly in the advanced SoC node, and when you need a bigger memory size to store more data. Okay. And if you want to use external flash to solve the memory size issue, the interface here is prone for hacking. And some SoC added additional IP block to do on-the-fly encryption decryption, but it adds the extra cost, complexity, and die size to your SoC. Okay. So here is a Winbound solution. So our Trust Me secure flash platform can solve the limitation. So I'm going to use this system as an example. So in here, we have external Trust Me secure flash as your non-volatile storage to store your secret, your data. This way, your SoC can be designed without using expensive embedded technology. And the security flash here, being external, is easily scalable to fit to different requirements or application using the same SoC. Okay. By doing this way, your SoC has a complete freedom to use any technology to optimize your cost, your performance, your power consumption. Okay? And most important of all, the platform, the solution here, has passed the common criteria, EAL 5+ security certification, making it ideal for e-payment or similar secure application. So the bottom line here is that this solution here, the security performance of this system here, is essentially same as using the embedded flash solution. But it's just cheaper, it's just more flexible. So this is my last slide. I want to just share with you Winbang's so-called this portfolio solution for the AIoT application. So we have a product, have a different level of security, and for the application from the node to edge to cloud center, but we focus on the edge side because more and more the so-called processing or the AI is now being processed at edge node. Okay, and I think this more or less concludes my presentation, and I thank you for listening.
Thank you very much, Mr. Su, for your insightful talk. Thank you very much. Ladies and gentlemen, next, let's shift our focus back to Foundry again. It is my great pleasure to introduce our next speaker, Mr. S.C. Chen, co-president of UMC. Mr. Chen possesses more than 30 years of semiconductor R&D experience. He joined UMC in 1989, and throughout his 28 years at UMC, he has led multiple functions within the company, including advanced technology development, specialty technology development, customer engineering, and more. Prior to his current position, Mr. Chen was UMC's Senior Vice President. And now, ladies and gentlemen, please welcome Mr. Chen.
Yeah, good afternoon, ladies and gentlemen. It's my honor here to represent for the Foundry, to talk about the Foundry solution for the intelligently connected world. I think this one means that the, that's the AI IoT, okay? Yeah, this is the outline of my talk, okay? No, I talk about technology solution, but actually I'm not going to go deep into the technology detail. First, I'd like to go through the market trend first and talk about the application trend. And then I would like to talk about the semiconductor content, okay? How that enable the AI IoT, okay? To drive in the AI IoT improvement, okay? And last one, I will talk about as a Foundry, okay? What is our solution to enable the AI IoT? First, I think this is a very common chart, okay? To talk about the economic, the industry trend, okay, from the PC internet, okay, and to the mobile cloud area, and then go to the IoT and then AI IoT, okay. I believe this chart is very familiar to everyone. But from this chart, I think there are two key messages here, okay. The first one is that for the new AIoT big data era, that the AI will be everywhere, okay? If you look at the chart, that obviously we all know that the AI will be in your personal device, your smart home, your car, okay, and even in the industry application. And the reason for that is because all the hardware and software to support the AI is continue to innovate it, to improve, to make this happen. And the second one is that the AI has been driven by the technology innovated in our industry. For example, the device processing power has been improved so well in the past years. And also the software continue to be improved, okay? And because the hardware becoming much and much lower cost, okay? And also the big data become available. I think those factor actually is driving this transition into this AI, IoT era, okay? And as a member of this industry, we should be all proud because in the past 20 or 30 years, we have been performed so well to pushing to follow the Moore's law. That's why the performance get improved so much, the cost get reduced so much, so that can enable this technology migration. I think this one is just to show you that the AI system spending will be 10x growth in the next 5 years, okay? And AI has become very popular and widespread because, for example, that the personal assistant, the VPA, like Amazon, Alexa, Apple Siri, or Apple's face recognition, and Google Assistant. Those actually is helping this AI gadget widespread very quickly. I think this is also the AI spending, but followed by industry. The top 3 AI spending industry is the banking, financing, and then manufacturing, and then retail. When the first time I look at this chart, I say, why banking is the number 1? Okay, but I think everyone knows that the security for the banking is becoming a big risk. So that's why they invest the big money to save their money, okay? And then the next one is the manufacturing. I think that means the industry 4.0 or the smart manufacturing. And why it is becoming so important? And because this is a very high return of investment. Because if you invest the money into the smart manufacturing, you can easily improve your productivity, okay, and save your cost. So that's why people heavily invest into this manufacturing area. And if we look at the automotive and healthcare, those two are also a very high potential application, okay, to catch up. Okay, I think to support the overall AI infrastructure, you need to have 3 layers, from cloud to networking, and then to the down level, that's endpoint. Let me explain the 3 levels. The first one is the edge, that's the endpoint device. Mainly that's for the IoT and personal device, okay? The key is that these devices will have sensor to collect data, and then do the real-time data inference. And then transfer data to the middle stage, that is the networking. Sometimes people call it cloud edge, okay? This is for machine-to-machine communication. And it will do the real-time data processing and do the basic analysis. And then transfer the data up to the cloud. And then cloud will do the big data analysis, processing, do the deep learning, machine learning, etc. I think this chart is just to show you that the blue portion means that this is for the AI integration chip, okay? That means the AI integrated chip will be the mainstream to integrate more IP to enable the AI. Next, I will talk about the semiconductor content in the AI IoT device. To support the AI, you need to have many kinds of hardware to support it. Here I listed the top 10 hardware for the AI. I also put this into 3 categories. The first category is mainly to accelerate the computation performance, which are processor like GPU, TPU, ASIC, and FPGA. And the second one is like high performance computing, like in supercomputer infrastructure. And the third one is communication networking. And the second category, we call it AI-enabled endpoint, which means that you need to have a sensor, okay? So that with the sensor, you can enable your endpoint device to have AI function. The device can be the personal devices, connected home devices, and surveillance. And the last one is the AI autonomous endpoint. For this category, it will require sensor and also AI processor to support autonomous function. The hardware including the drone, robotics, and automotives. Then I will give you some of the example, okay? The first one is the BPA. That is a famous one like Amazon Alexa. In this hardware, from the component device within this device, you can see that there's a sensor, which is a microphone. And then you need to have some device to do the audio amplify, ADC, and DAC, okay? And then you need to have an application processor to do the processing the data. And also you need to have the connectivity device like Wi-Fi, Bluetooth, okay, and PMIC. And if you look at the technology used in this chart, most of them are just the mainstream technology, okay? And because the mainstream technology is becoming so available and cost so low, so that enable this one become available to most of the people that can have it. Okay. The next one is the facing recognition surveillance device. Again, you need to have a sensor in it, and this sensor is mainly the CMOS image sensor. Okay, and then you need to have a processor with inference engine. Again, you need to have the wireless LAN and Ethernet for communication. Okay, again, if you look at the technology used, also that's all the available technology. The third one is the autonomous driving. For this one, you will see more sensors are used. For example, you need to have camera, LiDAR, and ultrasonic sensor, and radar, okay? And also you need to have a very powerful engine because you need to do the AI for the engine processing for autonomous, okay? And this example is an IoT gateway. It will connect to the cloud and then down to the IoT device. And if you look at the device component within this gateway, those are just one processor, CPU, and then connectivity through Zigbee, Bluetooth, and wireless LAN. Okay. I think these 4 examples just to tell us that most of the technology are already available to enable this IoT device already, okay? And of course, for the high computing power, for the auto engine control, that still require a very high-end device. This is just another example, okay? I don't want to go through, this is for medical. Sorry for the data, the color truncate. I think this one just add one more sensor MEMS for your health check. And this one is more complicated. This one is more for industrial robotic, okay? Here you need to have more complicated processing module. So you can see there is a processor using the logic mixed signal device, and then you need to have FPGA to handle more complicated AI processing. And as for the sensing, okay, you need also many kind of different sensing. And for the MCU, this one is mainly for the motion control. And so you have a motor driver to control the robotic motion. Again, you need to have some communication module, which is a wireless than Ethernet. Okay, I think that's just the example to show you that the technology is so well prepared to support AI, IoT. Lastly, I would like to present the solution as a foundry. As I said, that to support the AI IoT, you have to cover from endpoint device to networking and then to cloud storage. To support this, you need to have 3 pillars, okay? The first one pillar is technology. You need to have broad technology portfolio to cover the endpoint device need, the networking device need, and also the cloud, okay? And the second pillar is you need to have a manufacturing excellence, which means that you need to have high volume capacity and product line flexibility to support all different kind of device need. And the last one is the design support to enable customers' product. This is the technology portfolio from UMC to support the different device requirement. Okay, we support a device from the legacy from even 0.6 micron up to the advanced node 14 nanometer. If we look at the left side, that we provide different kind of device. For example, we have RF CMOS, millimeter wave to support the RF requirement. Okay, and we have a high voltage device to support the display, and embedded non-volatile to support the MCU. Also, we have the MEMS, okay, to support the sensor. Next, I'd like to show you about our manufacturing center, okay? For 300 millimeter, we have 3 12-inch fab, and early next year, we are going to add another one. That's the Mia fab from Fujitsu. And for 200 millimeter, we have 6 fab, okay? And we also have 1 6-inch fab to support a 3.5 compound. In total, we have 0.6 million wafer per month. And the last pillar, as I mentioned, you need to have a good IP support infrastructure to support the AI product. This is just some of the example to show you that there are some success story to use our technology. The first one is the smart city for share bike. This is an SoC chip, okay, including the GPRS, near-band IoT, and Cat M1, using the 28 HPC plus, okay, and that deliver a very good power performance balance, and also deliver a very superior RF CMOS performance. The next example is for artificial intelligence application. This application is for drone with surveillance for AI to do some inferencing. This is an ASIC chip, also using 28 HPC, okay, using UMC's fundamental IP and functional IP, and first-time success with very good year. The last example is for the autonomous. Okay, this is one of the chip in UMC, which is MCU used in ADAS with auto grade 1. The chip has been used in dashboard, infotainment, and digital signal controller. This is a 28 nanometer product. It's already passed the auto reliability and in high volume production. We already shipped more than 5 million units in the past 2 years. Finally, I'd like to use this page to summarize my talk. UMC will focus on the specialty technology to enable the AI OT. And we'd like to focus on the 4 segments: automotive, AI, IoT, and 5G, with the 3 pillars I mentioned, with the specialty technology and our excellent manufacturing center, and also with the IP support to enable this new IoT. Thank you very much.
Thank you, Mr. Jian. Thank you. Hearing from our industry leaders, it is not hard to tell that AI has been a very hot topic. And our next speaker, Dr. Art de Geus, is going to explore how AI is the fusion of everything. Dr. Art de Geus is chairman and co-CEO of Synopsys. And so he's already on the stage. I'm not going to waste any time. Ladies and gentlemen, please welcome Dr. Art de Geus.
Well, good afternoon, and this is a field where we cannot waste any time because everything is moving very fast. And so this was an incredible day. This morning we literally saw history by the people that had made history, but more importantly, that had had a massive impact on the advances of humankind in the last 60 years. And yet there's a feeling that the advances that are ahead of us may still be much, much larger than anything we've seen. And I would propose to you that we're in the midst of a force field that has 2 key components. One, continued massive advancements on the silicon, on the physical side, that support massive advancements on the software side. I'll be even more bold. For all the advanced chips, silicon is not meaningful without software. Software is not meaningful without silicon. At the heart of this is the question of impact. And so we saw a lot of pieces of history, so I'll add a few more in this to try to see what is it that makes this so important. Because we have now entered the age of smart everything, but smart is not a new concept. It started a long, long time ago, and if we put it in the human conditions history, we can see that things like finding the fire massively impacted our ability to cook food, digest it better. The notion of the plow and the horse domestication and the wheel changed agriculture so much so that people could produce more than they could eat, therefore brought about commerce and exchanges. And if you go to more modern times, printing press, steam engine, electricity, you saw a number of those a minute ago. What is interesting is if we look at the timeline of those, literally moving from thousands of years to centuries to more recently decades, and now, surprisingly, we are in a phase where the advances are moving in terms of individual years. I would propose to you that each one of these areas with super high impact had 4 key components to make it successful. The first one, some aha. I think Morris Chang called it an innovation. But innovations rarely work. You very quickly have to package them up with a lot of engineering to make things practical, which cost effort. And that in itself is not sufficient. You need to actually turn it into a tech-onomic result loop. In other words, it needs to have some benefits and impact, and if you're lucky, you will see the growth feeding itself. What is particularly interesting in technology is that invariably, more important than this is the conjunction of multiple ahas with massive amount of multidimensional engineering, and that is where you get the very big techonomic impact. This, in turn, can happen in many, many different forms. Of course, the physics, and we're all very well steeped in that, but also in biology or in the intellectual space where the same concepts hold. And so one that's particularly interesting is one where physical changes brought about intellectual progress. And of course, what I'm talking about is the printing press. Let me decompose it for you a little bit. For starters, it needed an alphabet with a limited set of basic building blocks, 26 letters specifically. It needed to convert that into movable, reusable types. It then needed the conjunction of ink that would dry fast enough, paper that was stable, all inventions. And last but not least, the screw press to bring it all together. Now, we often cite Gutenberg as the first one that did this, but the reality was in China already 500, 600, 700 years early, there were building blocks, printing blocks. The only challenge was the alphabet was so large that you couldn't reuse it all that well. Be it as it may, it brought about the Renaissance, which is absolutely an exponential impact function. And in about 50 years, there were 20 million books printed, which was a radical exponential growth for that time. Let's bring this a little closer and move a mere 500 years forward. And now, of course, where we arrive is at a new alphabet. We have reduced the number of letters to 2. We're still working to see if we can do less, but 2 is pretty optimal at this point in time. And we found, of course, a way to package this up in very basic building blocks. Combine that with lithography and planar silicon transistors, and all you need now is some really good design and, of course, the EDA tools to make that happen. And you here have the modern printing press. And they come in pretty buildings, and clearly Taiwan has a lot of printing presses. And of course, what we have seen here is a growth rate referred to as Moore's Law, or the impact, I should say, of Moore's Law that is unbelievably great. Now, the technology underneath this has continued to advance at extremely rapid speed. Here you see the first 500 chips, the initial designs, the active designs, and the tape-outs. And maybe the biggest surprise is the word FinFET, because Moore's Law is dead. We've heard now so many times, including, by the way, from Gordon Moore himself, who prematurely announced the death of the law that he set and that puts us all in movement. The impact has been clear, and a number of you have talked about it already. If you look at the growth rate of the semiconductor industry, you see a first phase that has a massive impact, and one could easily call the new age of computation. You see also a pretty massive technology downturn. Networking was overhyped, overbuilt. And you see a second downturn, which had nothing to do with technology, more recent. But during that time, the age of mobility came about, and it was actually a very fundamental technology that needed to be mastered, which is low power. We then got a time of fairly high ups and downs, and a lot of people said semiconductors are not going to grow. Too much mergers, acquisitions, consolidation. And yet here we are. IoT, immensely optimistic thinking, has found AI, which is absolutely incredible stuff. And this age of smart everything, I would propose to you, will have bigger impact than anything we have seen so far. Now, before I get there, what's behind it from an EDA point of view, as I'm supposed to talk about EDA? Well, the curves look similar, which is the productivity increases that we have seen in silicon have also been mirrored almost exactly by EDA, starting with the very first capabilities, circuit simulation, the SPICE program, still today a revered product, still too slow, still not accurate enough, but still used massively. Then layout and place and route came about really as the moment that computers were able to embrace graphics. And then came a very big shift. And we were happy, luckily I should say, to be started at exactly that time. We started in 1986, so the same time as a number of companies that have been talked about today. And there were 2 technologies that really took up at that time, both around the notion of digital design, digital simulation and synthesis. And I cannot overstate how big the shift was, because at that moment, the printing press became digital and design became massively digital. And synthesis was particularly important in the context of the foundry business, because what synthesis lets you do is not only start from a high-level description, create automatically a circuit, but by switching the libraries, you could decide to which manufacturer you wanted to go. With other words, it gave a certain degree of freedom that was essential for the success of the fabless age and the foundries. After that, I would propose to you that massive IP reuse was the single biggest enhancer to productivity. With that, we entered a whole different age, which is the intersection of hardware and software, with all the challenges of which one do you optimize, how do you optimize them together, and by the way, also the new challenge of security. We'll come back to that in just a second. You take all of these things together and you fuse these technologies. First thing you notice is there's not a single lesson learned in the past that you can forget. If you don't remember those things we discovered in the 90s, cross-capacitance, a real problem. If you forget that today, no chip will work. In other words, the results today are the cumulative results of everything learned. And in that sense, AI is an unbelievable new accomplishment that's built on this platform. Now, another way to look at EDA, and let me give you sort of the 30-second primer, is to look at it by virtue of the task set. The basic task set is, can you capture data on a computer? If you can capture it, can you model it? If you can model it, can you simulate it? If you can simulate, can you analyze the results? If you can analyze the results, can you optimize with it? And actually, these bottom four are called computer-aided design or computer-aided engineering. The minute you start optimizing, you enter a different space. You're now starting to change the circuits. If you can optimize really well, can you automate? And that is today referred to as electronic design automation. There's one more element in this set of equations that's absolutely relevant, and that is the systematic reuse of IP that has been pre-built, pre-verified, pre-tested, and of course, massively accentuates and accelerates the automation of design. Now, if you look at this, it's quite interesting that AI actually follows the same general structure. It starts with the very notion of capturing data through sensors typically, or in databases that you have already, structure this in neural networks, which is a combination of modeling and simulation and optimization. This learning process then yields a simulator that can be interpreted on new cases. This interpretation may drive limited actions or ultimately complete automation, such as autonomous driving, for example. And so the parallelisms are very visible. Yet there is a massive difference between those two worlds. The one that you see here on the right is fundamentally deductive thinking. If then else. This leads to the following conclusion. Yes, you too could do a simulation by hand. It would be very slow, but you could do it because your brain is capable of deductive reasoning. The one on the left is entirely based on the utilization of patterns as a way to guide to solutions. And what to me is so exciting is if we now can combine these two areas, we have fundamentally combined the two things that the human brain is best at, except the human brain is still way, 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 way ahead of anything we can do today. Ergo, there is a long road ahead. But in simple terms, you can see the applications today. Here's an aircraft engine. What people now try to do is create a digital twin, a model in other words, and then they apply both simulation to it and machine learning with the hope that they could diagnose early on if certain patterns are the hallmarks of, let's say, cracks in this engine, at which point in time you certainly do not want to do another flight with it. And that, of course, fundamentally changes the very business model that is touched by the combination of all of these technologies and has major economics impact on this entire industry. And therein lies the essence of my message. The economic impact is enormous of what we're going to do. Now, I mentioned simulation. Simulation, too, has had this unbelievable race of can you do things faster? Actually, the word simulation is synonymous for too slow. It's always been too slow. And yet, we have made enormous progress if you look at the number of cycles. One way to do that is to trade off between speed and accuracy by looking at different levels of abstraction. And traditional software simulations, very accurate, but relatively slow. Others can be much faster. And ultimately, where this is going is that hybrid simulation of a combination of many different approaches and levels of abstraction are combined to then make this possible, as we've seen enormous advances, both using software and hardware incarnations to get there. And the amounts of data and the number of simulations we want to do is absolutely astronomical. Now, to use an example that brings this all together, that is close to the fields, specifically in this area around advances in silicon technology, let me introduce to you DTCO, Design Technology Co-Optimization. The first observation is that, yes, we are still going to much, much smaller devices. Secondly, we are creating new device structures. Third, the number of materials that are being used are still being expanded on, and Mark Liu explained that very, very well. Well, in order to do that, you have to look at now the structures that we see here. And if you look a little closer, what do you see? You see individual atomic levels. Well, we would love to simulate these type of things to see how they behave when you build them. And traditional TCAD was essentially solving 3D Maxwell's equations. No longer good enough. And so, as of now, about a year, for the first time, we now have new technology. It's called ab initio, which is literally simulating from the atomic level representations using extremely fine meshing techniques and ultimately being able to extract electric parameters from this. And so the type of structures that we're now looking at literally look at the atomic level to understand how they will behave. So let's say we could do this. And partially we can, and partially we're still learning how to do it really well. Here's the ambition. The ambition is to say, well, if we are developing new technology, can we actually simulate the impact of new materials? Can we simulate the process? Can we simulate the lithography, which, by the way, is much less correct and precise than you may think? Can we simulate the new types of devices? And out of these combined simulations, can we extract the new parasitics? And that, of course, leads to the gradual automation of creating the combination of SPICE models and data rules, i.e. PDKs. Well, let's say we could. And if we did this now, what could we do next? Well, what we could do next is, from that, we can certainly do the cell development from that automatically. From there, we can use these cells and implement, why not, some ARM core or other relevant big block. And then ask ourselves the question, what if we made a change somewhere in this chain, and what would be the impact of this change be on the final product? Well, you can do this today. All you have to do is fabricate it. As we well know, that's an expensive and long road. But what if we could simulate? Well, if we could simulate, why don't we simulate a few more cases, and a few more cases, and a few more cases, and then, of course, apply machine learning to what we see there. Now, this is a complex road, but a number of the pieces are already being aligned, and this is where both simulation and machine learning will have massive impact on the future. So briefly summarizing what is around AI, I think there are four forces. The first two are highly correlated. One is big compute, massive compute. The other is amazing new machine learning algorithms. And they're massively connected, because if you are a machine learning algorithm, what do you think? I could be so much better. All I need is 1,000 times more computation. I'm not going to get that by just shrinking transistors. I'm going to get some of it. I'm going to get that by changing the architectures that sit in the middle. And the GPU was a good step in the right direction. Right now, there are dozens of companies building brand new extreme chips, all thinking that they have the ultimate AI architecture coming up. And some will, at least for a little while. The third ingredient in this is the availability and the structure of big data. You combine these three things, the impact is actually not there. The impact is going to be in vertical applications, in vertical markets. And the impact will be so big that it's not just optimizing things, we see many of those already, but it will change these markets. So just to put it in the right sort of deep feeling, let me introduce to you here the Greek god of semiconductors, Semiconductorius. And you look at this equation, you can see the bow is the power, the data is what we're going to use to ultimately go after opportunities, vertical markets, such as automotive, for example, and it will have big impact. Why automotive? Because automotive right now is being shaken up to its foundation, not just of what is a car, but who owns the car, well, where it be, how it will be transacted, and so on. And so let's look at automotive for a moment. They have just discovered that not only is electrification upon this, that's relatively straightforward, actually, except where you get the energy. But that autonomous driving will change the notion of what is a car. And autonomous driving sits in the middle of exactly this tension field of hardware and software. And the very fact that car companies today are considering having advanced FinFET chips in their cars is a bold step for an industry that has been relatively slow at adopting new technologies. But the other thing is, The entire car is shifting. Of course, we have 100 years of mechanical improvements, fabulous technology, amended by electronics, but now massively amended by software. And if you look at the amount of software in advanced cars, it has passed 100 million lines of code. No doubt, no bugs in that, I hope. But this is now the other challenge. You take these advances in silicon technology, you take the advances in semiconductors, and you look at the challenges. These have to be automotive ready and safe. And this is true for the silicon, it is true for the intersection between hardware and software, and it's true for what is happening in the software itself. So 3 quick examples of the type of things that will be happening in this industry. If you look at the silicon, and the foundries, of course, already massively working on this, so are we. Our EDA tools are now certified for automotive use. So is much of the IP, and that took a while. It is actually quite difficult to make large collections of IP ready for utilization in cars. This is just to give you a sense how long it took us. Others are working well on this. Secondly, the notion of virtual prototyping is absolutely essential. Because here's the challenge. Let's say you have a major subsystem in a car. This takes years to build, and it takes many more years to maintain as the car is on the market for 15 years and will be evolving in various ways. Well, this subsystem has a major architecture. Typically, what people do is develop it, and then gradually they make sort of boards that they can send around to the people developing the software in the hope that they get started and can debug it. And finally, you have the ultimate physical board or system. Well, it takes time because the chips take time to design, they take time to come back for manufacturing. So meanwhile, you want to get going on the software. So this is where simulation comes about. If you could have sufficiently good models of the chips, and you combine them with a model of the architecture and a model with the stimuli, you essentially now have a virtual board that you can copy and that you can send to all the people developing software. And therein lies the trick. Going forward, time to market, success of devices will be entirely dependent on the joint arrival of hardware and software, and by the way, being equally standardized for the risks that come with cars that actually can kill people. So the demands are going to be very severe, but ultimately the virtual boards, or the virtual prototyping, or models, if you like, will be the alternate path to actually pre-creating a device. The last one to briefly mention is security, and it came up with the gentleman from Winbond was very clear about all the challenges that are faced. And if you look at any system, you have inputs, sensors typically, you have outputs, maybe actuators, but pretty quickly you go from the physical analog mixed signal to the digital. You then pretty quickly are essentially in the electronics of compute, the compute to software, the software to proprietary code or open source code, and ultimately to the applications that govern your point of impact. The challenge is each one of these, especially when connected, is just attracting hacking like flies. And so it's in this context that we will need to pre-design and pre-verify and ultimately make sure that not only the hardware but also the software is safe from a safety point of view and from a security point of view. And here too our company is trying to invest in a number of things, all aimed at now the software side of this equation. So if I can summarize the points made so far, we're looking at a transformation that goes far beyond what we've seen in the past. Many of the examples we saw are great examples and clearly show that the opportunity space for semiconductors will continue to grow very much. But they're also very often continuations of things that we've done in the past. 5G is not fundamentally a different thing than 4G. It's just much better, faster, and unbelievably great engineering. But it is not fundamentally a shift to what we can do in mankind. You know, Paul had a great example of a head on a chip. Where this is going is chips in our head. I can predict right now, in 60 years, there will be many people with chips inside of their head. That is such a long distance. Already today, there's electronics interacting with brains for a number of situations. Already today, artificial eyes are providing data directly into the brain. These advances will continue, and the very fact that we are going to have a technical capability that will attempt to compete with the very capabilities that a human have is fundamentally changing the very nature of what a human is and what the world is about. So it's in that context that, yes, we have an unbelievable future ahead of us with some unbelievable challenges and unbelievable responsibilities of how we deal with this. But there's also no question that having this celebration here in Taiwan specifically 60 years after the first ICs came about, we can easily say, if nothing other big things happen in the world, that the technology opportunities are absolutely as large or larger than anything we've seen. And if somebody else writes the history of mankind in 1,000 years, they will point to this point as being just as important as some of the other big innovations that I've shown you. What is remarkable, and it was so remarkable seeing the people this morning, is that these big changes, physical, biological, intellectual, that we've seen recently, that we can put in the categories of computation, communication, and I would argue to you, not AI, but the very notion of cognition, the science of knowledge, what to do with that. These changes so far have been accomplished in the lifetime of people in this room. That is quite remarkable, and it is astounding how fast this is. With high speed comes great opportunities and great dangers. In any case, it also takes great passion to be successful. And if nothing else, in Taiwan, I think we find both the capabilities and the passion. And so to 60 years of IC, congratulations.
Thank you, Dr. RDGS. Thank you very much. Ladies and gentlemen, our next topic is packaging, and we're very honored to have Dr. Tien Wu, President and CEO of ASE, to share his vision on key aspects of future packaging technology and how they might open up new design concepts and business freedom to enable better performance and efficiency at the system level. Ladies and gentlemen, please welcome Dr. Tien Wu with applause.
Thank you. I always like Art's talk. He's by far the smartest person that I know. In all of his talk, I always learn wisdom. So today, we're here to celebrate the IC60. So to celebrate the IC60, I see no better ways to salute the people in this room. Because it is people in this room, our character, that made the industry, not the science, not the technology. So if I want to talk about the character of the IC people in this room, we have two types of people. We have dreamer. If you're not optimistic, you won't even consider to join this industry. I'm really talking to the student in the next room. But more importantly, you need to be a survivor. We are optimistic, but people in this room, we're goddamn tough. So to talk about the IC60 going forward for the next 60 years, I chose the topic of bridging the gaps. This morning, we heard plenty of people talk about it, how good the future is. But this industry is goddamn tough. When we talk about the good side of things, we should also talk about the dark side of things. The motivation is given by the absolute value of the gap between the good and the bad. If you do something, you get rewarded. If you don't do something, you get penalized. And that is the motivation for private enterprise, to the government, and to all the individual. So my talk today is bridging the gaps. Before my talk, I want to borrow what I learned from 佛经。心不自心，因境故心；境不自境，因心故境。The translation of that is, we see what we choose to see, because all perception is a choice. In what follows, I will talk about 4 gaps that concern our industry at large. In each one of them, you will see a challenge, a fundamental gap of the industry that we need to embrace and we need to solve. At the same time, we see tremendous amount of opportunity for people, enterprise, and alliance who can go figure out how to solve the gaps. So to begin with, let me talk about the Moore's Law and the value of semiconductor. Many people talk about this. We're so used to this chart. As a matter of fact, we're used to a point. We do not draw new information from this chart anymore. But let me ask you two questions. This chart says that in each technology node, we make incremental investment. The incremental investment, yes, slowing down, getting bigger. We got that. But in every single technology node, in every single year, the new investment comparing to the overall investment we have made in the past 60 years is very small. How can you make such a smaller, relatively speaking, incremental investment, but you drive the complete value of the ecosystem up? Question number one. Question number two. When the technological node, Moore's Law, or the effective Moore's Law slowing down, what is the impact in the future to this curve? If you're optimistic, you will say that, don't worry about it. The industry always figure out by itself. If you're not so optimistic, you will think about, well, what about LED? What about solar? When there's no incremental investment, when there is no innovation, when there is no efficiency, everything becomes commoditized and the whole industry stops. Well, I'm here to talk about this because this is what I worry every single night. I don't worry about it. What if the Moore's Law continue? Then there's no problem to solve. If the business is so good and there is no issue, I will only talk about it. What if, in any case, things does not go as planned in Taiwan? This generation, people in this room, what are you going to do about it? Technology and competition, those are the two things that we love. We're optimistic about technology because we're engineers. We hate competition because it's brutal. But technology and competition, they serve the single purpose of our industry in an identical way. They make us better. So embrace innovation. We must have innovation. Embrace competition the same way we embrace innovation. So don't hate your competitor across the ocean, across the channel. Love them. Love them in a unique way. We're going to talk about it. Technology and competition does the following. It drives two efficiencies. Technology, if I do it simple way, technology only serves one purpose. It drives energy efficiency. By design, by materials, by processes, anything. Competition does only one thing, your cost efficiency, not pricing, cost. Technology make us more cost effective. Competition make us more cost effective. Technology make us more design and energy efficient. So in this chart, what I've demonstrated over the last 50 years, you can see that we have two large migration. SoC integration driven by technology and competition. At the same time, the SoC efficiency and the price competitiveness in turn drives the system consolidation, efficiency in both ways, as well as volume of sales. It is a combination of this complex ecosystem. You have fierce technology competition, you have fierce price competition. Therefore, it drives new system, new application, new volume, new sales. And therefore, it drives all technology sales, including legacy and incremental new product. If we fail to understand this, you'll only talk about it. Well, what is the big deal of no 5 nanometer, 3 nanometer? TSMC is going to make less money. No, it is not the case. When you're losing the driver, you're losing the energy efficiency, you're losing the cost efficiency, therefore you will lose the system cell and the motivation to invent new application and new system volume. And therefore, the whole ecosystem collapsed. That is the dark side of it. One of the ways I like to do is, because I'm here to talk about the packaging future, let me use packaging as an example. In this simple chart, you can see two sides. You can be optimistic, you can be pessimistic. This chart showing the technology nodes, the value of semiconductor, as well as the gap between the leading foundry technology nodes and the leading packaging technology nodes. As you can see that in the last 48 years, the gap between leading foundry and the leading packaging changed around 50 times to 1,600 times. If you're optimistic and you look at it, well, packaging doesn't need to do anything. We just sit here and wait for the technology node, Moore's Law. We will get the elevation of the overall value for the packaging industry. But if you look at the flip side of it, what if the Moore's Law slows down? How should packaging embrace the gap, leverage, capitalize the gap? Is it cheaper to become a cheaper investment to create alternative energy and cost efficiency to complement or augment the Moore's Law? Software, firmware, everything that you do, materials, process, equipment, automation, you got to think about the same question on this chart. I'm giving you an example. A GPU in the PCB board. In the first quarter, we reduced 66% to become a module. And you are familiar with that module. We reduced another 30% into a low power, embedded, passive and active module. In a simple way you look at it, well, it is smaller form factor, it's more efficient, it's lower cost. But the implication of this chart is a whole lot deeper than what I just said. Because at a PCB stage, whatever you do is only for the graphics. When you go to the module, it becomes a server chip. When you go to the low power embedded, it becomes an artificial intelligence chip. If I really want to ask you, who is using the artificial intelligence, I really cannot name any large application. But what I can tell you for sure is Bitcoin. For the last 3 years, this become a leading supplier to drive the whole blockchain, artificial intelligence, data mining, and cryptocurrency. A brand new industry was created because the energy and the cost efficiency. Now, you can multiply this example by 1,000 times, but the industry is really an aggregate of this kind of efficiency, cost, and energy, therefore, in turn, drives the application, therefore, in turn, drive the volume sale of the system. That makes the value of the ecosystem. So today, we're not just talking about a foundry, we're not just talking about packaging, we are actually talking about a global semiconductor ecosystem, and that is the carrot and stick. From the company's end, we are building the following things. On this chart, what you can see is we are really preparing for a technology building block, not for today, but in the next 5 to 10 years, all of the IoT, low energy, microsystem, they will need a lot of building block. Okay, that's one message I want to impress you with this. But the second message is even more important. When we're doing data processing, computing, memory, you have a global standard. And Taiwan is fantastic when we have a global standard. We just do cost down. We use cost, scale, we kill everybody. But in what is going forward, when you think about AI, when you think about artificial intelligence, smart city, finance, medical tech, autonomous driving, you are getting into every single country and government's heart. You're not going to get a Taiwanese standard to sell your autonomous driving in Munich. I can tell you that for sure. The tariff war between US and China is to compete on who control the standard and the right to do first business. So going forward, our mindset needs to switch. We have to deal with multiple standards in autonomous driving, multiple standards in AI, multiple standards in every single thing you do. Now, in that regard, you cannot rely upon the Taiwanese IP invented in Taiwan for the world. That does not work anymore. As an example, what I can tell you now is the AEZ is a lead-frame automotive low-power solution, ASE joint venture with Infineon. The organic substrate is called CSOP. It's another joint venture between ASE and Japanese TDK. I can go on and on the sensor MEMS with Bosch. Fan-out will be with Cypress, Qualcomm. What is going forward is in the next generalized effective universe, Taiwan packaging community needs to embrace IP from all over the world in order to devise something that can meet the standard unique requirement of volume, low volume, very high mix around the world. That is the message. Now, let me talk about business alliance. I think the worst part of this is now, who's going to get the money? Hardware is getting cheaper and cheaper. If the hardware does not create an intrinsic flexibility to meet the future demand, then the software tuning will define who gets the value. Today, you can complain about Apple, you can complain about Google, you can complain all of the software guys, but it doesn't really matter because it's the hardware guys. We did not create the intrinsic flexibility to meet demand in the world. But let me be honest, if the hardware guys can do this, it will be more costly, more cost effective. So this is the kind of thing going forward. We have to understand that there's a big consolidation and the convergence. The system guys, the IC guys, the packaging guys, and the EMS guys, eventually they'll become one. They might not be one entity, but they will be one giant alliance where people will deal with everything circled in the blue box. Design know-how, ownership and liability, and the worst part, margin allocation. Listen, in semiconductor, yes, we're working on the dream. You know, we're dreamers, we're idealists, but be honest, we're here to make money. If we're not here to make money, none of you will be here. We need to understand the issues in the center, embrace it. In the business alliance, what I call is the next level of enlightenment. If we apply the past knowledge about alliance, what is fair, what is not fair, you are still at this level of enlightenment. We need to migrate to the next level in order to see how do we resolve the gigantic conflict of interest between hardware, software, between business ownership, liability. But before I get into any of this, we must be very big and we must be very profitable. Otherwise, you don't even get to talk to others about how do we form this gigantic business alliance. So the future OSAT values, I just list a few items that we're working on with all of our ecosystem and partner. Form factor, fan-out, panel fan-out, microsystem, SIP, heterogeneous integration. We talked many times about this. Low power, 2.5D, 3D, embedded, active, and passive. In my simplistic view, there's only one problem in the world, is power. Everything you do is all about power. To have a power supply from peripheral to go all the way to the center and go back, it simply doesn't make any sense. Eventually, the power needs to go vertical. Ideally, if you can embed like the neurons, the memory, the CPU, everything, the sensor, is all within one cell. Until you can do that, we have to solve the first order problem is a vertical supply of power. And that's what we're working on right now. The cross-functional, that's what the ART, that's what the Cadence is doing. The integrated design platform and service with a cross-functional domain knowledge is critical. I need to do a little advertisement here. Art talks about the future, right? The quantum, the atomistic, great. We will continue to plunge that. But let's take one step backwards. On the MEMS, on the sensor, on the passive, on the embedded, we have a much lower level problem we can solve today. So the question is not about who is more technology advanced. The right question to ask is, where is the goddamn bottleneck that stops us from making money today? If you believe that heterogeneous integration is one of the bottlenecks, the EDA guys, you should dedicate 1/3 of your company to work on the heterogeneous integration, because that's where the money is today. And by the way, when you think about IoT, when you think of autonomous driving, how many people will really need 3 nanometer? And what is the percentage of 3 nanometer in the gigantic percentage of the overall silicon that is required? But at the same time, at a system level, if you do a smart architecture, if you do a smart cross-functional domain knowledge design linked to the manufacturing yield, how much money can you create today? The quality must be artificial intelligence assisted. I cannot give you more, but ASE's got 3 light out manufacturing factory, and we're really working 10 years, and we're not even there yet. It got to be embraced, the artificial intelligence and design automation, because the quality requirements in the future are completely different. When you deal with memory, CPU, there's no consequence. No people will die. Autonomous driving, medical science, finance, government, smart city, infrastructure. In each one of them, the quality requirement is 100 to 1,000 times more stringent. Every single material, process, quality, defect needs to be machine tracked, machine learned, machine documented. Unless you have a light out, automated factory, you don't even do that part of the business. All of this investment needs to be 10 years before the business actually happens. There are very few companies willing to make that investment to make the AI, to make the infrastructure, to make all of the building blocks. And in Taiwan, we're doing this. High-mix, I talk about it. It will be a standardized SIP module, SIP system package module for the cost. And there will be a software tuning. And I hope hardware guys can accommodate most of the tuning. Otherwise, that 10% software tuning will capitalize 90% of your profit. Efficiency and cost, Moore's law plus all other bottlenecks. I do not know where are the bottlenecks. We pick a few, right? Each one of you should pick your own. The business alliance, I call the higher level complexity and also the comprehension. I want to spend some time talk about this chart. This chart is very dear to Taiwan. This is the market share of the whole ecosystem global. I have 2 colors. I have the green color. Green color is the rest of the world. Red color is China. The Green Party marks the equilibrium of the last 60 years. We've been doing this together, like a brother and sister who grew up together. We hate each other, but we're so used to each other, we don't even feel the hatred anymore. So in the green part, we never complain. You never complain about Korean DRAM. You never talk about how powerful Americans are. We just love each other because we understand. Whatever you do, I don't do. Whatever I do, you don't do. Now, there's a new player coming, it's called China. All of a sudden, everybody feel like, well, how come? There's no room for you. But the Chinese are here. They present tremendous amount of market opportunity. Therefore, we have to invite them to the dining room. But to begin with, they're doing fabulous 15%, foundry 10%, OSAT 17%, and consumption 42%. That's tied more to the population. Now, in this space, Taiwan feels threatened because how come? Whatever I do, you do that too. Whatever I don't do, you don't do. So we're face-to-face, hand-to-hand combat. Therefore, we feel threatened. And this is being felt by the enterprise as well as the government. But let me offer you the flip side of the story. China does not view Taiwan as the target. China views American as the target. So 20 years from now, let me give you another landscape. What China will show is they will have a lot of IDMs. They will have a lot of tools, Fabless and foundry and OSAT are merely a vehicle and a jumping board to achieve the greater good, which is IDM tools and everything else. Think about it. If you are the Chinese leader, do you want to kill Taiwan or you want to dominate the world? Okay, now that's their aspiration. I'm not saying they can do that, but if you believe that is the way, let me give you another hypothesis. If China can indeed get 20% tool and 20% IDM, what does that mean? They're not going to do something better than Applied Materials today. They're not going to do something better than Intel today in microprocessor. If China can really come up in tool and IDM, that means they figure out multiple layers of new innovation like Bitcoin. It is something good for China. It is something better for the world. So to think about semiconductor, to begin with, you cannot think about country, company, region, individual. You got to think about the world. Whatever is better for the world in the long run on energy and cost and lifestyle, and that will be the area you choose to do. And that is something I've learned over the last 40 years. Always do the right thing. Do not be myopia or parochial. Only think about what about me. You got to think about what about the world. And this is only a very small example of it. With that, I want to give you a summary. Semiconductor future is bright. Demand for everything is great. I don't need to talk about this anymore. Moore's law remains critical. Come on, guys. Moore's law pays our salary. Don't always talk about Moore's law slowing down. It is not slowing down. We have some execution detail we need to walk through. We talk about maybe some complementary, more than more, but our hope is we would like to do packaging, firmware, software, everything else to make sure the effective momentum of Moore's law stays on the curve. Conflict of interest and competition among regions and business entities also present great opportunity for us to embrace at the same time. And the last, not the least, play to win. I borrowed this term from the Crazy Rich Asians. If you have not seen that movie, go watch it. Play to win remains the only unchanging rule in the semi-jungle. The nature of the jungle has never changed. It never changed in the last 60 years. It won't change for the next 60 years. Thank you.
Thank you, Dr. Wu. Thank you. Our next speaker is Dr. Richard Gacho, Executive Vice President and Corporate CTO at Lam Research, who will explore the future of smart tools and semiconductor fabrication. Ladies and gentlemen, please welcome Dr. Gacho.
Good afternoon. I'm really happy to be here this afternoon and to share this stage with the industry greats that were up here earlier today. It's a tremendous honor to participate in such an event. It's also
现在无所不在，未来无限可能。台湾的远见写下半导体的传奇，60年的影响力奔转全世界，机体电路的浪潮将继续勇往直前。
IC60邀请您一同参与。这个惊天动地的发明默默的发生，当时连发明家都无法预测它的重要，即使产业先锋看到它的潜力，当时他们也无法想象这个发明居然会给世界带来这么巨大的影响力。第一片进入市场的机体电路其实只有10颗电晶体，但是它却淘汰了占满整个房间的大型电脑，并且造就商用电脑的兴起，启动了真正的资讯时代。当美国宣布登月计划的时候，美国太空总署的火箭技术还远远不如苏联，但是美国所拥有的是1000颗电晶体的机体电路技术，让电脑可以缩小到公事包的大小， 足以装在阿波罗太空船上。虽然以我们现在的标准，它比较像是计算机，不像是真正的电脑，但是没有那一台电脑，要成功登陆月球，再安全返航是根本办不到的。基底电路成了太空竞赛最关键的优势。当万颗电晶体整合出了微处理器，在低能见度时，飞机可完全依赖电脑自动降落。机器人还不太能走路，不过给了我们前天后的领前功能。除了计算，电脑也可以开始画图，甚至制作简单的动画。到了10万颗电晶体，3D 动画问世了。除了线条，它也可以呈现光影的模拟。机器人依然不太会走路，但是在生产线上，我们随处可见机器手臂，为我们打造高品质的汽车。当扩增到100万个电晶体时，电脑走入了家中。到了1000万个电晶体，基底电路帮我们连接了整个世界。当基底电路拥有10亿个电晶体，电脑开始无形化，变得无所不在。60年的发展，我们又到达了关键的时刻。电晶体的体积小到临界点，或许我们已经无法继续缩小下去，但是摩尔定律的精神会用其他形式无止境的延续。我们将再度踏入电脑进化的新革命，届时世界又会变成什么新面貌？我们还在持续想象，因为对于未知，对于未来，我们永不设限。
现在无所不在，未来无限可能。台湾的远见写下半导体的传奇，60年的影响力奔转全世界，机体电路的浪潮将继续勇往直前。
IC60邀请您一同参与。这个惊天动地的发明默默的发生，当时连发明家都无法预测它的重要，即使产业先锋看到它的潜力，当时他们也无法想象这个发明居然会给世界带来这么巨大的影响力。第一片进入市场的基底电路其实只有10颗电晶体，但是它却淘汰了占满整个房间的大型电脑，并且造就商用电脑的兴起，启动了真正的资讯时代。当美国宣布登月计划的时候，美国太空总署的火箭技术还远远不如苏联，但是美国所拥有的是1000颗电晶体的基底电路技术，让电脑可以缩小到公事包的大小，足以装在阿波罗太空船上。虽然以我们现在的标准，它比较像是计算机，不像是真正的电脑，但是没有那一台电脑，要成功登陆月球，再安全返航是根本办不到的。基底电路成了太空竞赛最关键的优势。当万颗电晶体整合出了微处理器，在低能见度时，飞机可完全依赖电脑自动降落。机器人还不太能走路，不过给了我们前天后的领前功能。除了计算，电脑也可以开始画图，甚至制作简单的动画。到了10万颗电晶体，3D 动画问世了。除了线条，它也可以呈现光影的模拟。机器人依然不太会走路，但是在生产线上，我们随处可见机器手臂，为我们打造高品质的汽车。当扩增到100万个电晶体时，电脑走入了家中。到了1000万个电晶体，基底电路帮我们连接了整个世界。 当机体电路拥有10亿个电晶体，电脑开始无形化，变得无所不在。60年的发展，我们又到达了关键的时刻。电晶体的体积小到临界点，或许我们已经无法继续缩小下去，但是摩尔定律的精神会用其他形式无止境的延续。我们将再度踏入电脑进化的新革命，届时世界又会变成什么新面貌？我们还在持续想象，因为对于未知，对于未来，我们永不设限。
现在无所不在，未来无限可能。台湾的远见写下半导体的传奇，60年的影响力奔转全世界，机体电路的浪潮将继续勇往直前。
IC 60邀请您一同参与。这个惊天动地的发明默默的发生，当时连发明家都无法预测它的重要，即使产业先锋看到它的潜力，当时他们也无法想象这个发明居然会给世界带来这么巨大的影响力。第一片进入市场的机体电路其实只有10颗电晶体，但是它却淘汰了占满整个房间的大型电脑，并且造就商用电脑的兴起，启动了真正的资讯时代。当美国宣布登月计划的时候，美国太空总署的火箭技术还远远不如苏联，但是美国所拥有的是1000颗电晶体的机体电路技术，让电脑可以缩小到公事包的大小，足以装在阿波罗太空船上。虽然以我们现在的标准，它比较像是计算机，不像是真正的电脑，但是没有那一台电脑，要成功登陆月球，再安全返航是根本办不到的。机体电路成了太空竞赛最关键的优势。当万颗电晶体整合出了微处理器，在低能见度时，飞机可完全依赖电脑自动降落。机器人还不太能走路，不过给了我们前天后的领钱功能。除了计算，电脑也可以开始画图，甚至制作简单的动画。到了10万颗电晶体，3D 动画问世了。除了线条，它也可以呈现光影的模拟。机器人依然不太会走路，但是在生产线上，我们随处可见机器手臂，为我们打造高品质的汽车。当扩增到100万个电晶体时，电脑走入了家中。到了1000万个电晶体，机体电路帮我们连接了整个世界。当机体电路拥有10亿个电晶体，电脑开始无形化，变得无所不在。60年的发展，我们又到达了关键的时刻。电晶体的体积小到临界点，或许我们已经无法继续缩小下去，但是摩尔定律的精神会用其他形式无止境的延续。我们将再度踏入电脑进化的新革命，届时世界又会变成什么新面貌？我们还在持续想象，因为对于未知，对于未来，我们永不设限。
现在无所不在，未来无限可能。台湾的远见写下半导体的传奇，60年的影响力奔转全世界，机体电路的浪潮将继续勇往直前。
IC 60邀请您一同参与。 这个惊天动地的发明默默的发生，当时连发明家都无法预测它的重要，即使产业先锋看到它的潜力，当时他们也无法想象这个发明居然会给世界带来这么巨大的影响力。第一片进入市场的基体电路其实只有10颗电晶体，但是它却淘汰了占满整个房间的大型电脑，并且造就商用电脑的兴起，启动了真正的资讯时代。当美国宣布登月计划的时候，美国太空总署的火箭技术还远远不如苏联，但是美国所拥有的是1000颗电晶体的基体电路技术，让电脑可以缩小到公事包的大小，足以装在阿波罗太空船上。虽然以我们现在的标准，它比较像是计算机，不像是真正的电脑，但是没有那一台电脑，要成功登陆月球，再安全返航是根本办不到的。基体电路成了太空竞赛最关键的优势。当万颗电晶体整合出了微处理器，在低能见度时，飞机可完全依赖电脑自动降落。机器人还不太能走路，不过给了我们前天后的领钱功能。除了计算，电脑也可以开始画图，甚至制作简单的动画。到了10万颗电晶体，3D 动画问世了。除了线条，它也可以呈现光影的模拟。机器人依然不太会走路，但是在生产线上，我们随处可见机器手臂为我们打造高品质的汽车。当扩增到100万个电晶体时，电脑走入了家中。到了1000万个电晶体，基体电路帮我们连接了整个世界。当基体电路拥有10亿个电晶体，电脑开始无形化，变得无所不在。60年的发展，我们又到达了关键的时刻。电晶体的体积小到临界点，或许我们已经无法继续缩小下去，但是摩尔定律的精神会用其他形式无止境的延续。我们将再度踏入电脑进化的新革命，届时世界又会变成什么新面貌，我们还在持续想象。因为对于未知，对于未来，我们永不设限。
现在无所不在，未来无限可能。台湾的远见写下半导体的传奇，60年的影响力奔转全世界，机体电路的浪潮将继续勇往直前。
IC60邀请您一同参与。这个惊天动地的发明默默的发生，当时连发明家都无法预测它的重要，即使产业先锋看到它的潜力，当时他们也无法想象这个发明居然会给世界带来这么巨大的影响力。第一片进入市场的基体电路其实只有10颗电晶体，但是它却淘汰了占满整个房间的大型电脑，并且造就商用电脑的兴起，启动了真正的资讯时代。当美国宣布登月计划的时候，美国太空总署的火箭技术还远远不如苏联，但是美国所拥有的是1000颗电晶体的基体电路技术，让电脑可以缩小到公事包的大小，足以装在阿波罗太空船上。虽然以我们现在的标准，它比较像是计算机，不像是真正的电脑，但是没有那一台电脑，要成功登陆月球，再安全返航是根本办不到的。基体电路成了太空竞赛最关键的优势。当万颗电晶体整合出了微处理器，在低能见度时，飞机可完全依赖电脑自动降落。机 机器人还不太能走路，不过给了我们前天后的领钱功能。除了计算，电脑也可以开始画图，甚至制作简单的动画。到了10万颗电晶体，3D 动画问世了。除了线条，它也可以呈现光影的模拟。机器人依然不太会走路，但是在生产线上，我们随处可见机器手臂为我们打造高品质的汽车。当扩增到100万个电晶体时，电脑走入了家中。到了1000万个电晶体，基体电路帮我们连接了整个世界。当基体电路拥有10亿个电晶体，电脑开始无形化，变得无所不在。60年的发展，我们又到达了关键的时刻。电晶体的体积小到临界点，或许我们已经无法继续缩小下去，但是摩尔定律的精神会用其他形式无止境的延续。我们将再度踏入电脑进化的新革命，届时世界又会变成什么新面貌？我们还在持续想象，因为对于未知，对于未来，我们永不设限。
现在无所不在，未来无限可能。台湾的远见写下半导体的传奇。60年的影响力奔转全世界，机体电路的浪潮将继续勇往直前。
IC 60邀请您一同参与。这个惊天动地的发明默默的发生。当时连发明家都无法预测它的重要，即使产业先锋看到它的潜力，当时他们也无法想象这个发明居然会给世界带来这么巨大的影响力。第一片进入市场的基体电路其实只有10颗电晶体，但是它却淘汰了占满整个房间的大型电脑，并且造就商用电脑的兴起，启动了真正的资讯时代。当美国宣布登月计划的时候，美国太空总署的火箭技术还远远不如苏联，但是美国所拥有的是1000颗电晶体的基体电路技术，让电脑可以缩小到公事包的大小，足以装在阿波罗太空船上。虽然以我们现在的标准，它比较像是计算机，不像是真正的电脑，但是没有那一台电脑，要成功登陆月球，再安全返航是根本办不到的。基体电路成了太空竞赛最关键的优势。当万颗电晶体整合出了微处理器，在低能见度时，飞机可完全依赖电脑自动降落。机器人还不太能走路，不过给了我们前天后的领钱功能。除了计算，电脑也可以开始画图，甚至制作简单的动画。到了10万颗电晶体，3D 动画问世了。除了线条，它也可以呈现光影的模拟。机器人依然不太会走路，但是在生产线上，我们随处可见机器手臂为我们打造高品质的汽车。当扩增到100万个电晶体时，电脑走入了家中。到了1000万个电晶体，基体电路帮我们连接了整个世界。当基体电路拥有10亿个电晶体，电脑开始无形化，变得无所不在。 60年的发展，我们又到达了关键的时刻。电晶体的体积小到临界点，或许我们已经无法继续缩小下去，但是摩尔定律的精神会用其他形式无止境的延续。我们将再度踏入电脑进化的新革命，届时世界又会变成什么新面貌？我们还在持续想象，因为对于未知，对于未来，我们永不设限。
现在无所不在，未来无限可能。台湾的远见写下半导体的传奇，60年的影响力奔转全世界，机体电路的浪潮将继续勇往直前。
IC60邀请您一同参与。这个惊天动地的发明默默的发生，当时连发明家都无法预测它的重要，即使产业先锋看到它的潜力，当时他们也无法想象这个发明居然会给世界带来这么巨大的影响力。第一片进入市场的机体电路其实只有10颗电晶体，但是它却淘汰了占满整个房间的大型电脑，并且造就商用电脑的兴起，启动了真正的资讯时代。当美国宣布登月计划的时候，美国太空总署的火箭技术还远远不如苏联，但是美国所拥有的是1000颗电晶体的机体电路技术，让电脑可以缩小到公事包的大小，足以装在阿波罗太空船上。虽然以我们现在的标准，它比较像是计算机，不像是真正的电脑，但是没有那一台电脑，要成功登陆月球，再安全返航是根本办不到的。机体电路成了太空竞赛最关键的优势。当万颗电晶体整合出了微处理器，在低能见度时，飞机可完全依赖电脑自动降落。机器人还不太能走路，不过给了我们前天后的领钱功能。除了计算，电脑也可以开始画图，甚至制作简单的动画。到了10万颗电晶体，3D 动画问世了。除了线条，它也可以呈现光影的模拟。机器人依然不太会走路，但是在生产线上，我们随处可见机器手臂，为我们打造高品质的汽车。当扩增到100万个电晶体时，电脑走入了家中。到了1000万个电晶体，机体电路帮我们连接了整个世界。当机体电路拥有10亿个电晶体，电脑开始无形化，变得无所不在。60年的发展，我们又到达了关键的时刻。电晶体的体积小到临界点，或许我们已经无法继续缩小下去，但是摩尔定律的精神会用其他形式无止境的延续。我们将再度踏入电脑进化的新革命，届时世界又会变成什么新面貌？我们还在持续想象，因为对于未知，对于未来，我们永不设限。
Ladies and gentlemen, last but not least, we will explore the topic of materials. We're very honored to have Dr. James Frey, Business President of Dow DuPont, to give his talk titled The Age of Contrast, Expanding Markets and Converging Technologies. Please join me in welcoming Dr. Frey onto the stage.
3 mics going here at once, so I'm sure you got to be able to hear me this afternoon. Good afternoon. I'm very happy and very honored to be here. We saw a lot of pioneers of the industries, fathers of the industries, heroes of the industries over the last 60 years, so I'm very honored to be presenting. I almost feel like a newbie having been only 32 years in this industry, so I guess I've got a lot of years left to go. But I can move these aside here. Our industry is on the cusp of profound and exhilarating change. With digital transformation, mobility, and connectivity expanding towards new markets, while technology is converging into new applications, enabling smaller and smarter devices. It's a very exciting time to be in this industry. The smartphone has evolved from a large brick phone we call back in the 80s, to something that's very small and thin, mobile, and quite capable, eventually becoming the gateway into a world of Internet of Things, 5G, and artificial intelligence. So it's a very exciting time to be in the industry. I'm going to talk today a little bit. I want to start with an introduction to Dow DuPont, my company, and talk a little bit about Dow DuPont. And Dow DuPont actually is a rather new company. It's the merger of Dow and DuPont over the last year. And in fact, it's probably going to disappear in probably the first quarter next year, where we'll actually be separating into 3 separate companies. So I assure you that the electronics and imaging part of that business will be retained as a whole. I want to talk a little bit about new applications and some of the industry drivers, a lot of which you already saw today, so there's going to be a lot of reoccurring themes. But then I want to move into the role of electronic materials and how materials, and from a material perspective, I believe has played a very important part in the evolution of our IC industry over 60 years. So Dow DuPont, the electronics and imaging business, is made up of the merger of Dow Electronic Materials and DuPont Electronics and Communication, and actually Dow Corning Electronic Materials as well rolled into that. We're made up of 5 separate businesses. One of our largest is a semiconductor, which encompasses all our materials for lithography, the imaging type materials, as well as the underlayers, the removers, etc. CMP business, both pads and slurries, the advanced packaging chemistries, as well as the EKC business, which again is strippers and removers, so a rather large business entity. We also have a large circuit board business, which encompasses both imaging and metallization chemistries for producing circuit boards, the photovoltaics, both the metallization as well as the backsheet materials, advanced printing, and finally display materials as well, all consumable materials for making the displays. So a rather large portfolio, about $5 billion in size. So it makes us one of the largest electronic material portfolios out there. A very broad and diverse material set allows us to help with our customers integrate these technologies in a wide variety of applications and devices. We're about 6,000 employees and about 64 sites around the world. A large part of that is in Asia. A very large contingent of that is actually in Taiwan. So we have a very large presence here over quite a long period of time. Some of the global market trends we've all talked about here. These are mega trends. The environment is certainly a big driver for a lot of our industries, a big driver for a lot of the industries out there in the Dow DuPont portfolio as well. From renewable energy, automotive, whether it's hybrid vehicles or true EV vehicles or autonomous vehicles, LED and more efficient energy sources. Emerging markets and urbanization. China is still growing at a healthy 6 to 8% GDP. Still a lot more consumers buying more and more of electronics. India is growing with their use of electronics, as well as other continents like Africa, etc. So continued urbanization means continued electronic consumption. Healthcare. With an aging population, this is a growing mega trend out there as well, but really growing in the preventative area. So we're seeing a lot of insurance companies invest in preventative health care. So we're seeing a lot more electronic devices to measure your heart rate, your body temperatures, et cetera. So there's a lot of investment and a lot of driver coming from the healthcare industry. Connectivity, the Internet of Things, we keep talking about that. Smart cities, smart homes, going into your home where your home recognizes you, automatically adjusting your house temperature. your refrigerator replenishing your favorite beverages and foods when it goes down, your lights automatically adjusting to your likeness. Enhanced user experience such as augmented and virtual reality, continuing, it's moving from a kids gaming to basically an employment tool. We're going to start going to meetings with virtual reality headsets on, and we won't have to travel anymore. And conferences like this actually might be all of us at our home environments with headsets on, attending great conferences like this. And finally, artificial intelligence. Something we talked more and more here today. Something that's not really brand new. In fact, the first concept of artificial intelligence is from the mid-50s. Sort of had its rise in the 50s and kind of went away. But back these days, because of more and more data and more computing power, it really is becoming a reality. So that important artificial intelligence, an interesting study done by KPMG in 2016 and 2017. They interviewed a lot of members of our industry about what would have the most influence or most impacts on the industry in 2016 and 2017. Some of the usual ones like smart home and mobile, industrial, automotive, robotics and drones, consumer electronics, all pretty obvious. But what's interesting is the change in artificial intelligence. In 2016, it showed up about 18% of effect going on to 2018. But in 2017, that number was 43%. It's becoming more and more important, and I would propose that in the same study was done this year, that would grow up probably 60+%. So artificial intelligence is becoming more and more popular, more and more, as we've seen all the presentations today, more and more mainstream. Artificial intelligence promises a new era of disruption and productivity. And human ingenuity is enhanced by speed and precision of artificial intelligence. The question is can AI change the basics of the economic value creation? And I know that question has been asked a lot in many economic forums. The traditional model of worldwide GDP encompasses the capital efficiency, labor, and productivity. In the past decades, the average GDP has actually decreased. Capital efficiency, which is an indicator of capital productivity, also on the decline, as studied by the European Commission. In fact, it's been on the decline for over the last 50 years. And finally, productivity, a key measure of how well the economy uses its existing capital. A study by Accenture shows that's also been in decline over the last 10 years. Artificial intelligence has a potential of stopping that and, in fact, reversing that trend and increasing the economic growth in the world. AI is evolving from a hot new trend to a seamless enabler of business transformation. AI is poised to be the industry's new nervous system. Look at some of the market trends and applications that AI can affect, including IoT, 5G, big data, cloud computing, blockchain, as we heard earlier in the day, artificial reality as well as virtual reality, mobile, all the way up to smart factories. AI will have a dramatic influence on all these technologies. AI will drive semiconductor growth and innovation. By 2021, all premium smartphones are forecast to include AI functionality. By 2022, 5% of all the new vehicles will have such AI capabilities, with high volume manufacturing achieved and starting in 2020. And by 2022, according to Gartner, more than 50% of enterprises will deploy AI accelerators. The question is, what does this mean for our semiconductor industry? The chart on the right shows the semiconductor revenue growth driven by AI. It is forecast to increase by more than 200% from 2017 to 2022. More performing AI processors and more accelerators will be required. Integration of multi-die packaging will increase. Processing moving to the edge. Finally, all of these AI accelerators will also require high bandwidth memories. So we'll have a dramatic impact on our semiconductor industry. By 2020, 50 billion devices will be connected by 4 billion of the population. Just look at some of the daily use. The average internet user will use about 1.5 gigabytes of data. The average autonomous vehicle, 4 terabytes of data. A connected airplane, 5 terabytes of data. A smart factory, 1 petabyte of data. 1 petabyte is equivalent to 223,000 DVDs of about 4.7 gigabytes, if any of you guys are still using DVDs. And finally, there will be 750 petabytes of data provided by cloud video providers. Tremendous, tremendous amount of data. Obviously, we're going to need a faster means of transferring and transporting this data around. The answer to that is 5G. Going from 4G to 5G, I've heard the best comparison, it's like going from a typewriter to a computer. 5G is the 5th generation of telecommunications. It's a new era of interconnectedness. It will impact every industry from automotive, healthcare, and manufacturing. 5G is as revolutionary as the advent of electricity, as well as the advent of the automotive industry. Let's look at the evolution of wireless technology and the upcoming road to 5G. All the way back to 1G, the first generation, back in early 1980s. This was the brick phones, and I grew up on a show called Magnum PI, and I still remember fondly Magnum would always pull out his brick phone, which was the size twice the size of your hand. Really only had analog and voice capability. That was it. Moving on to 2G, where we moved into the digital modes, a little bit more faster speeds and more security, but still quite slow. 3G and onto 4G LTE, where we had a lot of mobile internet users on the 4G mode. 5G is able to send and receive messages at the same time, which is very different than the 4G mode. It allows multiple wavelengths from Wi-Fi to higher frequencies. Of course, we've heard of lower power consumption from 5G, faster speeds to move the data, lower latency on the order of 1 microsecond, and the ability to connect more and more devices. Although we talk about the IoT today, the Internet of Things, and connecting all our devices, reality is you're not going to be able to connect them in the 4G world. In the 5G world, you will be able to connect multiple devices at the same time. The best part about 5G, I think, is actually being able to download a high-definition 3D movie in less than 4 seconds. That would take you almost 2 hours in a 3G communications. The basic fact is 4G just does not have the capacity for the New World Order. 5G is like the oxygen for autonomous vehicles. In a 5G world, drone delivery will actually be a reality. Smart cities, a reality. Smartphones, even more powerful than they are today in the 4G world. Remote surgery. Top-notch surgeon in London performing remote surgery on a patient in New York City with no lag time, of course, no latency. Gaming will be absolutely incredible in a 5G world. So a 5G world would be very, very different. A lot more materials required, a lot more conductors, better insulators, if you will, as well. Semiconductor adoption will continue to grow in a variety of markets, from communications, consumers, data processing, industrial, and automotive. We're already seeing telematics increasing in number in automotives as we start looking at more advanced cars. In a hybrid mode or electric vehicle, we're going to see more and more electronics, more chips, more wires, etc. 5G will require new devices to leverage these new capabilities. That's good for the electronics industry as a whole. 5G will drive up economic growth. It's estimated that to build a 5G infrastructure in the United States alone, it's $300 billion. On a worldwide basis, that's over $1 trillion investment. So it's going to be great for the economy. Over the past six decades, the computing trends have dramatically evolved. From mainframes in the early 60s, where performance was really the primary driver. As computing power moved into a consumer world, cost became very, very important. As it moved into the mobile and internet world, miniaturization was also important. As we move up the computing capability into smartphones, IoT, AI, et cetera, we have more and more deliverables. Cost, performance, power, size, latency, bandwidth density, faster time to market, et cetera. So more and more of these capabilities required. More and more challenges as well as we get more materials and heterogeneous integration going on at the same time. So a lot more material challenges. Let's look at some of those material challenges in we'll start with the chip side. If you look at lithography, all the way back in the I-line and G-line era, we had bis azides and cyclic olefins. Moving to the I-line where we had novolacs and diazonaptoquinones, onto DPV where we had the polyhydroxystyrene derivatives and chemically amplified materials, into the 193 world, both dry as well as immersion. Our materials changed again, and we had these blocky copolymers, pentapolymers, adamantane type molecules, going all the way down to directed self-assembly and EUV. Our materials have gotten purer, but much more complicated in designing. At the same time, a lot of ancillary materials, such as removers and strippers, top coats, bottom anti-reflector layers, top anti-reflector layers, et cetera, all advancing in those, helping with those design constraints and the Moore's Law as well. But the integration of those materials provided a lot of challenges over time. At the same time, CMP came into be mainstream in sub-quarter micron, both slurries and pads. Again, also all had to be integrated into the material sets. So the material sets have gotten more and more complicated over time. The integration of these materials and designing them to make them work together have become much more challenging. Moore's Law has also driven innovation across the entire supply chain. On the device side, the silicon side, the shrinks have outpaced the shrinks on the organic and panel processing. As a result, there's been a pretty substantial gap between those two. What has addressed that gap is a lot of the advanced packaging designs, all the way from the lead frames, through hole, all of the chip scale packaging, system and package, all the way up into the fan-out SiP modules, et cetera. So there's been a lot of advanced package designs, a lot of different companies getting involved, a lot of semi-companies getting involved in the advanced packaging design to address this gap. If you look at the packaging design itself, some of the material sets, the integration, very challenging. On the metallization side, the copper redistribution layer, the copper pillars, copper through silicon via and copper damascene processing, tin silver bumping, tin silver capped copper pillars, low temperature capped copper pillars, et cetera. So a lot of metallization technologies have been designed over the years to make the advanced packaging capability. On the organic side, same thing. We had the photoresistor imaging for imaging these vias and the chemically amplified materials, liquid photodielectrics, dry film dielectric materials, permanent bonding materials, non-conductive films, and thermally insulated, thermally management materials as well. These chips, as we know in the packages, generate a lot of heat, so a lot of organic materials have been designed to manage that heat. So putting all these materials, designing them to address the roadmap, but also integrating them into these advanced package design, very difficult, very challenging. If you look at the board side, equally as challenging, both from an imaging as well as a metallization perspective. Wide range of materials and processes are needed for these developments. Final finishes, dielectrics, laminates, copper metallization processes, EDTA-free electroless copper, electroless as well as electrolytic type coppers, a lot of different metallization, different metals, different plating capabilities, chemistries, substrate preparation. You know, you need to etch these films and these substrates to actually get them to perform and to metallize. We're looking at high frequency, high speed laminate type technologies. As we move into 5G, those are more and more important. So the evolution of the substrate, the evolution of the board has also been equally daunting and equally challenging. Also, over the last 32 years that I've been in this industry, and probably even longer, green chemistries, more sustainable chemistries have made it more challenging, but also more rewarding for us. Safe solvents for photoresist. The solvents, I would just say, are very different than they were when I was working with them about 30 some years ago. PFAS and PFOA-free lithography chemistries. lead-free solders, moving into tin silver, formaldehyde-free plating baths, cyanide-free gold plating baths, EDTA-free materials, and even the latest cadmium-free quantum dots for the display chemistries. We're committed, I think the industry is committed to safer, greener chemistries, and it's becoming more and more challenging, but also more rewarding. I keep getting asked the question, when are a lot of these new technologies such as 5G and AI coming to the world? The answer is actually it already started. 5G, there's a very strong investment over the last couple of years for 5G infrastructure all around the world. If you visit anywhere in China, the US, and Europe, 5G is happening. Artificial intelligence, I think if you have an Alexa at home or a Roomba or a smart thermostat, you already see the examples of AI already out there. New materials and integrated technologies are really at the heart of these future connected worlds. Both Dow and DuPont really had a culture of innovation, and that's something we're going to continue as we continue our merge, as we continue to split off in later time. Collaboration is another big key. We've collaborated with our customers and all the members of the supply chain, and I think we would recognize as an industry the importance of collaborating to make these technologies possible, to make these devices possible, and to enable 5G and Internet of Things. Finally, the future for materials is still very, very exciting. I actually wish I was 20 again, because I think as we start looking at this new world with 5G and Internet of Things and AI, very exciting time to be in this industry. A lot of materials required, all new materials. With 5G, we're probably going to all have to replace our devices at home, so there's a lot more business out there. Very exciting time to be in the industry. Finally, thank you very much.
Thank you, Dr. Frey, for your insightful talk. Thank you so much. Ladies and gentlemen, that concludes IC60 Master Forum. We thank you very much for your generous participation, and we do hope that you find today's forum very rewarding. We wish you a very happy and a great Semicon Taiwan 2018. Have a lovely day. 今天 IC 大师论坛到此告一段落，非常感谢大家的参与，请大家离开的时候不要忘记您的个人物品，并且记得归还翻译耳机。再次欢迎大家的莅临，预祝大家在 Semicon 台湾拥有丰硕的成果，预祝大家有愉快的一天，谢谢。